Try to record in this computer while people think about questions. And I'm going to get my stuff set up. Okay, so Dr. Miller has office hours on Mondays. Perfect, right? So that's going to be really nice. Okay. Okay, so let's get started today. We're going to finish up special relativity and then start off on quantum mechanics. And note that the quantum mechanics part, I don't expect you to have done the even the quantum mechanics chapters in your modern physics class or your third semester physics class. But hopefully they at least gave you some conceptual understanding what quantum mechanics is about and how we can move forward with mostly covering review. So what I'm going to do is I'm going to actually cover those chapters in this textbook I sent to you guys called Modern Physics by Survey. It's based on that. But if you have your own modern physics textbook, use that one, right? Whichever chapter they corresponds to. Okay. So previously, right, we have another type of four vector. It's the energy momentum four vector, or more commonly known, it's just going to be the momentum four vector, right? Even though it has this little energy in it, but energy is going to be wrapped into this momentum four vectors, right? And then so this is the contravariant, and then we have the covariant, which was the index downstairs, right? What should I write on the next three components here? Is it just px, py, pz, or is it something else? Right, we negate all the spatial component in the convention for this particular textbook, right? That way, when you do the dot product between the two using the Einstein notation, where if you have the same indices on the same side of the equation, you multiply those two numbers together one at a time and add up all the different indices, right? So in this case, right, we have E, the first index, right, square, and then the second index is px squared, the third index is py squared, the fourth index is pz squared, right? And this is index 0, 1, 2, 3, right? Another way to write this is just like write p square, right? Okay, so be a little careful. P square is not the same as the p vector square, right? Which is very confusing, right? Especially in the textbook where they just kind of have the bold print version of it, right? But if you're writing this on paper, you can just do this, right? Or put even an absolute value sign around it, okay? Okay, right? With this, just as what I talk about on Wednesday, right? Treat this four momentum vector, right, as if it's just momentum. It's just momentum, right? So let's say, we already went through talking about these different types of scattering diagrams, right? So you have, maybe a particle coming in here, an anti-particle coming in this way, right? Let's say a electron and a positron annihilating with each other, right? Then producing some other particles on the other side, okay? Just like momentum, right? Momentum is conserved. So in each part of these collisions, sorry for those of you on Zoom, right? You didn't see my parentheses, collisions, or just particles running into each other or getting close enough proximity so that they actually interact with each other, right? These collisions are happening at this point here, okay? So what you can say, if I can get rid of that white part, right, is that since this momentum is coming in here, momentum 2 is coming in here, right? The sum of those momentum is going to add up to whatever this Q momentum is, right? Just like if you had a car, with momentum 1 running into here, a car with momentum 2 coming in here, right? Whatever the rec is that's coming out is going to be the sum of those momentum, right? Like just as in introductory physics, okay? So in this case, the nomenclature, we call that Q, which is the momentum transfer between the two particles, okay? And the outgoing momentum also have to add up, right, to be Q, okay? In this case, because you have this going out, this going out. Whatever momentum is coming out here is going to add up to P3 plus P4, right? But this different for different diagrams, right? So this is the S channel. For the T channel, right? They're not colliding into each other. What you're doing is you have P1 shooting off some momentum Q off to the side, and then continuing on as P3, right? In this case, right, P1 plus, well, P1 minus P3, almost fell from my own trap, right, is the amount of momentum being transferred between the two particles, right? So in this case, the what's happening is that maybe you have a particle coming, a car going in this direction, and then maybe someone throw a baseball or something off on the side, right? We call that Q, right? And that actually pushes the car in a new direction, and therefore you actually have momentum 3. So momentum 1 minus momentum 3 is the Q instead, right? Similarly, similarly, the other side is P2 minus P4, right? You have P2, and then the ball's being thrown this way, and then you have the difference between the two momentum. Very similarly, the U channel, right, is the same thing as the T channel, but instead of P1 minus P3, you have to swap for P4, because remember P4 for the U channel, the P4, right, actually came from particle 1, right? Because you have an exchange of particles between the top and the bottom of the diagram, right? So this one's related to this one, right? This one's related to this one, okay? You're just exchanging 3 and 4, and then the last one is, this is supposed to be 3, yeah. So Shane just caught that mistake when I was typing, okay? Right, and the idea of constructing all these 4 momentum is that when you square them, when you dot product them, or you do the Einstein summation of their scalar product, right? Whatever their square is the Lorentz invariant, okay? And that's why we're going to call each of these 3 different channels a particular Lorentz invariant. The first one, that with the S channel, is going to call S, okay? And hopefully you can see that, right? The next one is going to be called T, and then the last one is going to be called U, right? It's just whatever momentum is here, right? If you take the dot product to itself, right, you get a Lorentz invariant. And for the S channel, we'll call it S. For the T channel, we'll call it T. For the U channel, we'll call it U. Okay? Okay. And this basically tells you how much momentum squared, right? Because all of this is basically just Q squares, right? Depending on which one you're talking about. Okay? It's the momentum transfer between the particles, okay? It's the momentum of whatever this particle is, maybe most of the time it's going to be a photon, okay? So that'll give you the momentum of the photon exchange between 2 particles. It could be a W, it could be a Z, right? Whatever that is, okay? So let's do a special example, because, this is happening 25 million times per second in a country, well, in Geneva, where they're smashing proton and proton together constantly, basically about probably 12 hours a day, okay? So in Geneva, there's this thing called a Large Hadron Collider. So I think most of you probably heard a little bit about it, but you may not know how it actually works. What they do is they smash 2 protons together. Actually, what they're doing is smashing like billions of protons together and hoping some of them will hit each other, okay? But in this simple version, right? Let's say I have a proton coming in here, right? I'm shooting it with momentum P1. I'm shooting it in exact and opposite direction with momentum P2. Okay. P1, right, is the energy of the first proton. And let's say this is the Z-axis, right? And so all the momentum is in the Z direction. And then the energy of proton number 2, right, is going to be E2, and then just momentum 2. Okay, if they're going in exact opposite direction of each other, and let's say they have the same momentum but equal and opposite each other, right? That means P2, right, in the Z direction is going to be equal and opposite P1 in the Z direction. Okay, in this case, it makes a very interesting calculation for this S channel, because you have 2 particles running into each other. That's basically this diagram up top, right? You have 2 particles running into each other, right? They're not scattering off each other like in the T channel or the U channel. They're literally smashing into each other, okay? So when we do this calculation, well, P1 plus P2 squared, right, is going to be whatever the energy of those 2 particles summed up together squared, okay? But it's also going to be subtracted by their 3 momentum squared also, right? But in this case, the 3 momentum of these two particles are equal and opposite each other, so this term is actually 0, right? So in this case, the total, well, the momentum transfer squared between these two particles, actually the energy of the first particle, the energy of the second particle square. So this is why, right, when we have collisions like this, we're actually more interested in square root of S. Square root of S is just going to be E1 star. Let's just, we have the same notation as they do. This is just kind of like the 3 momentum magnitude, okay? Because they're broken up into, I don't think the E actually needs it, because the star here, right? Remember the star, P star means the magnitude of the 3 momentum, not the 4 momentum, right? You don't actually need the star here, but the book decided to do it, so I'm just going to follow that, okay? Well, of course, if you square root both sides, then you just end up with the energy of particle number 1 plus the energy of particle number 2, okay? So at the Large Hadron Collider, the energy they're smashing these, each of these beam is going to be 6.5 TeV. TeV is 1,000 times a GeV. So, and the same thing on this side, they both have the same energy. So when you have this added up together, you have 13,000 GeV of energy that you're smashing into each other. Okay, just to give you guys a scale, right? Remember 1 GeV is approximately the mass of a proton, right? So they're smashing these protons together about 13,000 times more than its rest mass, okay? Okay, in terms of energy. And so all these are basically going at like 99.999999999% of the speed of light in the rest frame of the lab, okay? And this way, and the one thing to know is that, well, whatever energy comes in, right, it has to go out. And so what you can actually calculate if you have smashed 2 protons together and you're able to reconstruct or measure all the stuff that's coming out of it, the momentum of that event should add up to 13 TeV, right? Because whatever goes in has to go out, right? Just as, so the P1 plus P2 on this little S diagram, right, is the stuff that's kind of the 2 protons coming in. P3 and P4, right, in a sense, if they're like other particles, those particles could decay into other ones, right? And that will make, hundreds and maybe even thousands of other particles that comes out. And that's how, and if you add all those up, it should add up to, square root S, right? And that's how we figure out whether or not, maybe some event has missing energy in it, some energy disappear. And for a collider experiment like this, that missing energy tends to be either something we don't understand, or it could be, is most likely just going to be a neutrino, okay? Where these experiments do not actually measure the neutrino because they're not able to detect them, okay? Any questions about these? These are called Mandelstam. What do they call them? Mandelstam, yeah.
Mandelstam, yeah.
Mandelstam, yeah. Variables, okay. It's all these interesting European names, right? Okay. If there's no question, or while you're thinking about questions, I'm going to introduce the next section, right? So we're going to start this. We're not going to be able to finish it. In fact, we're going to spend the entire next week on this one section in the textbook, okay? Because what I'm doing is I'm basically taking this one section and say, wait, they didn't cover this, so I'm going to take an entire chapter in my modern physics textbook and stick it in there, okay? So we're actually going through, I think, like 2 chapters in the modern physics textbook in this, okay? But this is a pretty famous picture. I think maybe some of you seen this. This is a picture from, what was this, like 1927? It's called the Slovak Conference, where a bunch of, people who are studying at least the fundamental natures like smaller, quantum mechanics and special relativity all meet to just talk about what's going on and in their work and share and then collaborate and figure out how physics can move forward in 1927 at least. Okay, so you may recognize some of these people here, the little face in the middle, right? Even at that point, I think he is pretty famous, right? This guy. What's his name? I always forget his name. It's fine. The person I want to highlight is actually this guy in this case. His name is Max Born, and we're gonna use the Max Born interpretation, actually known as the Copenhagen interpretation, because that's where he worked, the city where he works, on quantum mechanics. Okay, and let's just state what the Copenhagen interpretation on quantum mechanics is about. Well, quantum mechanics is a probabilistic. It makes probabilistic predictions no matter what you do. Okay, it's always going to be probabilistic at the fundamental level. Okay, and this probabilistic nature, is going to occur at a small number of particles, meaning 1, 2, maybe 100, right? But as you get more and more ensemble, meaning you're dealing with thousands, maybe millions, or 10 to the 23 particles, right? They approach what's known as the classical mechanics limit, right? This is the stuff we learn in general physics. So, F equals ma. You can, push a 1 kilogram block in this direction. It'll accelerate, and that entire object will move as one, right? That's the classical limit. Okay. Right. So that kind of makes sense. Okay. Yeah, you have a bunch of probabilities, but then, if you average all these different, all these different probabilistic nature of particles, right, then it all kind of averages out. Okay. Because some particle may move faster, some may move slower, but the average tends to be what we see in large scale, meaning a kilogram, right? Like maybe just a gram even. Okay. Some of it is a little bit less intuitive, right? There's also the Born rule. Okay. And this is where people started thinking, okay, how do we deal with the mathematics between what we write down on a piece of paper versus what's actually happened in reality? Okay. The Born rule created these wave functions. Okay. Every particle, every object, everything, not just particle, like this entire table, me, the computer, or the signal that's being transmitted from my computer to your computer, all of those are systems of particles, systems or particles, right? And the wave function is going to postulate that it contains all the possible information that you ever need in order to figure out what's going on with that. So it describes the entire thing. Okay, and so what does that mean? Okay. But then when you make a measurement on the system, okay, the system interacts maybe with some sort of detector device, okay? In mathematical language, well, in the paper language, right, these are going to be called operators, and they turn out to be matrices. But let's just, think about when you interact with a device, what's going to happen is that the system, also known as the wave function, right, the system can be described by a wave function. It's going to collapse into some eigenstate with an eigenvalue, where the eigenvalue is actually what you measure. Okay. All right. So it's pretty abstract so far. And then let's try to make sense of it. Okay. By basically going through 2 chapters in a different textbook. Okay. So yeah, as I mentioned, I'm going to interweave a lot of Survey's Modern Physics textbook into this, alongside Thomson's Modern Particle Physics book. Okay. So by the way, right, I think I noted this, right? Survey's Modern Physics textbook. You don't have to buy it. If you can figure out how to get it, right? Or someone else can tell you how to get it. Okay. So in the Born interpretation, right, or the Copenhagen interpretation, right, we have these things called wave function, and the symbology of these is these psi's. Okay, this is some Greek letter, psi's, capital psi here, and in a particular representation, in the spatial representation is actually could be a function of space and time. Okay. And it's actually when you integrate it over all space and time of your concern, that's when you actually can calculate the probabilities of maybe finding a particular particle at a particular place, position, you're measuring the position, or maybe you're measuring the momentum of that particle. So you can actually, oh, it's going at 5 miles an hour or whatever the number is, right? You can measure its momentum, you can measure its energy, you can measure maybe a spin, you can measure a lot of different things. But the probability of you finding that particular particle in that state, right, is going to be this wave function square, but then integrated over all the space that you're making that measurement in a particular box or your detector sensor size. Okay. And this wave function can be, some funky thing. Okay. In fact, I think what's plotted here is actually the wave function square, because the wave function itself could be negative, right, in some place, or it could be, it's also complex, so it has some imaginary parts to it also. Okay. Right. So how do we deal with something like this, right? Okay. The way you deal with something like this is to not try to solve for the wave function, is to basically break up the wave function into little pieces, okay? And hopefully, at least some of you may have seen some of this in even your general physics, even if you didn't see it in modern physics, is that if you have a wave, okay, that is periodic, it doesn't have to be, say maybe it's like this, but it's periodic. I'm trying to draw it periodic, right? Where it kind of repeats itself over time. Okay, right? What you can do is you can add up a bunch of sines and cosine functions on top of it, right? You add them up. Maybe there's one like this and there's one like this. If you add up a bunch of them, okay, you can actually reproduce the original function pretty well, okay? This is known as a Fourier transform, okay, of a function, okay? But the main idea is that instead of trying to describe exactly what the function is, right, you're describing different wavelengths of it or different frequencies of it, okay, depending on which space you're dealing with, okay? And the way you would do this mathematically is that you have this thing called e to the I, right? This is the Euler's equation, kx minus omega t, okay? This is basically equal to cosine of kx omega t minus, plus in this case, right? Cosine of kx omega t, okay? So this is just a sum of sines and cosine functions. So whenever you see e to the I something, it's just a combinations of sines and cosine function, right? Okay. So just imagine this is some wave here that you're dealing with over here, okay? The thing in front of here is the coefficient for that particular wavelength. So you notice that this is a function of k. So for each wavelength, there's a different coefficient, right, that's associated with it. Because, well, let's do a simple case. I think we kind of did this in actually, what was that class in experimental physics, right? Where I think I drew this, where there was some wiggly thing like this. So this is some periodic function. And then I don't know why the thing decided to delete half the stuff I just drew, right? But you may recognize this as, well, it seems like there's some high frequency wave going on here, and then some low frequency wave. What you can do is actually break this up into two separate functions where, right, I have a low frequency part. Okay, whatever is happening is really annoying because it's just erasing itself all the time. Okay, I have some low frequency piece to it. You guys seeing this? Where it just disappears after I write it? Have this open somewhere else, that's why. All right, I'm gonna try a third time. Okay, let's see if it erases itself again. Making sure not to touch any buttons. Right. It just doesn't like the low frequency stuff. I'm gonna move it. Anyone has an idea why this? Now I can't erase either. So, okay, I'm gonna draw on top of this instead. Okay, so you have some low frequency part. Maybe it won't erase itself this time. Great. Okay, and then you have some high frequency part, right? Oops, I'm drawing the high frequency wrong. All right. Let's try this. Okay, the high frequency is actually just this piece, right? So if you add up the red and the black, if the software lets me keep my drawing, maybe I'm just squiggling too fast. I'll do it slower. Nope. Wow. I'm gonna just turn this off and turn it back on. Get rid of this stuff. Okay. Okay, here we go. I'm sorry? Oh, yeah, they shouldn't have that feature because I need to squiggle stuff. Okay, so if I squiggle stuff, then it erases things. Okay, that's really dumb. Because I need to draw squiggles sometimes, right? No one ever draws squiggles other than me. Okay, so I'm just gonna do the first few a little bit, okay? But imagine that blue line just keeps going, right? Okay. Anyway, okay, so the thing is, right, the black is actually the addition when you add, if you add the red and the blue together, you get the black function, right? Right, but each of these, right, the blue has a different amplitude. So this may be, k equals to 100. Actually, it's probably going to be a smaller one. Let's say 1, right? Where the red up here, right, has a different amplitude. Let's go to red, right? The red here has a different amplitude for k maybe equals to, so this is going to be a small wave number, right? Because that's momentum, okay? Right? So each of these has different amplitude, right? The main idea is that, right, each of these amplitude has to, right, be corresponding particular wavelengths that you're trying to add together. And, just think about, all these, whenever you think about integral, just think about, you're just adding up infinite number of things, right? That's the same thing as an integral. Okay, so what we want to do, okay, instead of trying to figure out the black function, why not just figure out each of the individual ones, right? Let's figure out the blue function. Let's figure out the red function by itself, right? Because at the end, what we can do is just add them together, right? This is the superposition principle that we use a lot in physics in order to solve very complicated problems, okay? So if we can figure out these coefficients a sub k, then we can actually determine the wave function of anything we want. So jumping back to Thomson once again, so this equation. So whenever you see equation like in chapter 6, that's from Survey. Whenever you see an equation from chapter 2, that's going to be from Thomson. Okay, that while each of these little pieces of the wave function is going to be proportional to the e to the I kx minus omega t, right? So it's just some sine and cosine wave. Okay, right? With natural units with h bar equals to 1, right? The k is basically the momentum because h bar is going to be 1. Okay. And then omega, right? Since the energy of a particular wave is going to be h bar times the angular frequency of it, if this is equal to 1, basically your wave function just turns into, right, some normalization, right, that's to be determined, right? That's basically kind of like the coefficient in front, right? E to the I, the momentum dotted into the spatial component of the wave function, right? And then the energy times the time, okay? So there's some waves that depends on the momentum, right? Basically the wave number depends on the momentum, and then the frequency depends on the energy of that wave, okay? And it's just changing with time, okay? And to me, this makes it so much easier to understand wave numbers and frequencies. So, you know, wave number is just the momentum, frequency is just the energy, right? Okay. So in order for us to use the Copenhagen interpretation, anytime we try to observe something, what we need to do is actually act on these wave function with some operator, okay? So typically maybe an operator A, I'm gonna put a little hat on top just to show that it's an operator versus just a number, right? And we're gonna have some wave function like this that depends on X and T. And then that allows us to measure whatever this A quantity is. So A could be, you know, position, A could be momentum, A could be energy, whatever you want it to measure. Okay. And what's going to happen is that when you make this measurement, right, it's basically going to collapse this wave function to a whatever that measurement A is, right? Let's say if this is the energy, right, this will tell you what the A is going to be the energy of that wave function. And then psi is going to collapse to some eigenvalue with that particular, so eigenvector with some particular of that particular eigenvalue. So what the hell is this eigen stuff that you're talking about? Okay. Eigen in German actually means, you know, one is like oneself. Okay. So, but we don't have to, you know, learn German to figure out how this works. So what I'm going to do is give you guys a concrete two-dimensional example of how eigenvalue, eigenvector actually works. So let's say I have some matrix. Did I maximize this again? Yeah. Matrix. I'm going to call it, you know, 1, 4, 3, 2. Okay. Just some matrix. Okay. Okay. And remember that these matrix is going to be represented by is actually trying to represent operators eventually. Okay. That we're going to be acting on these wave function to measure things out of it. Okay. So there's a procedure that allows us to solve these eigenvector, eigenvalue problems in your either math methods or your linear algebra book. I'm not going to go through that. But because the idea is that we're not trying to solve these eigenvalue, eigenvector problems. We're just trying to get the concept of why these eigenvectors and eigenvalues comes out, and it's very important in how we're going to measure things. Okay. So the idea of an eigenvalue, eigenvector is that you want this operator, this matrix, right? I'm going to interchange between the two a lot. Multiply by some vector, okay? And that's going to give you some number that is also proportional to the same vector. Okay, this is the same vector. Okay, remember in general, when you multiply matrices to a vector, it just changes the vector into something else, right? Like when we did Lorentz transform, right? Multiplying by the Lorentz transformation, right? Lambda, let's say x, right, turns it into like x prime, right? So these two vectors are different from each other in general, okay? But the idea of a eigenvalue, eigenvector is that these are special vectors, okay, that will allow, that are gonna make when you act on this with this matrix, it's gonna give you that something proportional to the original vector. It doesn't change it, okay? Okay, so the example here is that, well, the first eigenvector is actually 1, 1. Okay, it's not always going to be 1, 1. It's just by accident. So let's just make sure this is actually true. Okay, so if I do this matrix multiplication, so I take this number, multiply by this number, and then I take this number and then add it to this number. Sorry, let's just do it long form on the right. Okay, this is me just saying what I'm going to do. It doesn't help you guys, right? Okay. 3, 2, right? Okay. I know this is an eigenvector, but let's just see how it works, okay? So this is going to be equal to, okay, 1 times 1, right? So the top right is going to be 1 times 1, and then the next one is going to be 4 times 1, right? So I have to add 4 to that, okay? This element here, right, is going to be 1. All right, sorry, did I do that right? Oh, there is no second. That's why. That's why I was confused, right? Because this turns into a vector also, right? Okay. To figure out the second element here, right? You take 3 multiplied by 1, which is 3. You take this element, you take the second part here, multiply by this second part, then you get 2. Okay. So this multiplication gives you 5, 5. Okay. Obviously, that's not 1, 1, but it's proportional to 1, 1, right? So if you factor out this 5, you get 1, 1 back. Okay. So therefore, right, 1, 4, 3, 2. In this case, the eigenvector for this particular matrix, one of them is 1, 1. And then the eigenvalue for this particular eigenvector is 5. Right? Any questions? How many of you guys seen this before at some point? Okay, most of you guys. Okay. Or what about the folks on Zoom? I think.
I've seen it.
Yeah. Okay. So let's just complete the example. Okay, even though we're kind of taking a long time to do this, but that's okay. Okay. So in general, if you have a 2 by 2 matrix, you're going to have 2 eigenvalues. They may be the same eigenvalue, but there's at least 2 of them. Okay. Okay. So so the second eigenvector, I'm not going to try to solve it for you, but it's going to be negative 4, 3. So if you do the multiplication here, right, you're going to end up with the result of this multiplication is going to give you 8 minus 3. Okay, but that's not right. That's not right. That's negative 12. This is negative 6. Sorry. I'm fixing my mistake as I go along. Okay. Okay. 8, negative 6. Well, that's actually proportional to negative 4, 3, because if you factor out this negative 2, then you get negative 4, 3. Okay. So in this, the second eigenvalue for this matrix is negative 2, and the second eigenvector corresponding to the eigenvalue negative 2 is actually negative 4, 3. Okay. Right. So I went through that a little bit faster, but so hopefully in the homework we'll get a little bit of practice like this. Okay. So what does this mean in physics? Right. So doing a bunch of matrix math. What's the point of this? Okay. So for example, if that matrix, this matrix A, let's say is our energy matrix, right? Or also known as the energy operator for some system, right? What's going to happen is that, right, when we act on our wave function, let's see, right? If we measure the system with our operator A, which is measuring energy now, okay? What's going to happen is that it's either going to give us 5 as the answer, right? Right, which is the first eigenvector, eigenvalue, or negative 2 as the answer. Okay. So basically, if you act on your wave function here, right, it's going to be equal to 5 plus multiplied by the wave function, and this will be the eigenvalue eigenvector for that particular eigenvalue. Okay, I'm just going to label it 5. Okay, or right, there's 2 possible ways for this to come out. It could be negative 2 size up 2. Okay. Okay. So what's happening is, if you were to measure with this A operator, you either get 5 or negative 2 as the answer of the measurement. But what happened is that the wave function itself also turns into the eigenvector of that particular eigenvalue. Okay. Okay. Right. So in physics, so all these operators have to follow a certain rule. And I'm just going to state what the rule is. I'm not going to try to prove it to you. Okay. These operators has to be Hermitian, meaning they have to be a square matrix. Okay. It has to be, it's either, it could be 2 by 2, 3 by 3, right? 4 by 4. It can't be some irregular, it can't be like a 2 by 3 matrix, for example. Okay. Okay. And the fact that it's Hermitian means that its transpose conjugate is itself. So what the heck does that mean? Okay. So when let's do a 2 by 2 example. So let's say these are A, B, C, D are some complex numbers, right? So, okay. If I want to transpose it, okay, usually with the letter T, let's call this A, okay, just so we can get used to the language. Okay. A transpose is basically you flip the non-diagonal parts, okay, as if you just flipped it, okay? A So instead of B here, you get C, and then you get B here and D. Okay, you just kind of flip these two guys. Okay, everything's just off diagonal. Okay, so for example, let's do a 3 by 3, right? You know, I'm just going to put the same symbols everywhere, but just so I don't have to, let's just do it correctly, right? So let's say A, B, C, D, E, F, G, H, I, right? The transpose of that is going to be, all of this is going to be flipped to the other side with each other. Okay. I think I see people like staring at the screen, very confused. So that's why I'm going to actually do it. Okay. If you transpose this, let's call this B, right? B transpose. It's going to be, the diagonal stays the same. So I just copy that down. So whatever C is going to flip to the other side. And then that's going to exchange with G. And then B and D are exchanged with each other. If I can write that right. D, B. And then F and H are going to be flipped with each other. Okay. That's how you do a transpose. Okay. But not only that, it's also the complex conjugate. Okay. The complex conjugate of a matrix is just like a number that's a complex conjugate. It's just going to be, you negate the complex, the imaginary part of that value. Okay. B star, D star. Okay, that's the star. Okay, so example, if A is equal to X plus I, Y, right? The complex conjugate of that is X minus I, Y. Okay. Okay. Right. So combining these two functions together is actually known as the transpose conjugate, which has a special symbol because we do it all the time. It's called a dagger. It looks like a little dagger. So what you're doing is you're basically doing both. This is wrong. You guys don't catch me when I'm wrong, right? Because that's just the complex conjugate, not the transpose. Okay. A star, C star, B star, D star. Right. So you're doing both the transpose and the complex conjugating in one step with this dagger function. Okay. All right, let's just some examples of this. Okay, just so we can end up with some more physics examples, right? So if you want to measure the energy of a particular system or particle, right? The operator to figure that out is known as the Hamiltonian. Okay. I'm gonna define what a Hamiltonian is. I was hoping to do it today, but we'll probably have to do that on Monday. If you want to measure the momentum of a particle, there's the operators for momentum, Px, Py, Pz. If you want to measure position, X, Y, Z gives you the position, right? And the difference between the Hamiltonian, the position, and X, Y, Z is that instead of being a matrix of finite dimension, okay, these operators are actually infinite dimensional matrices. So that means I can't really just write it down somewhere and do the multiplication by hand. Okay. In case you just run into that in the future at some point, this is actually known as the Hilbert space, where you have infinite dimensional vectors with infinite dimensional operators that can act on these things to give you eigenvalue, eigenvectors. Okay. But like a finite example, okay, there's no is these Pauli matrices. Okay, this basically measures the spin of a particular particle. Okay, so the X Pauli matrix, right, is just 0, 1, 1, 0. Okay, that's what this matrix is. Okay, for this particular matrix, the eigenvalue is +1 or -1. Actually, for all three, it's actually +1 or -1. Okay. So if you want to figure out the spin of a particle in the X direction, you apply this operator, this matrix to it, and then you would either get +1 or -1 as the answer. And then the eigenvector that comes out that's associated with the +1 is going to be 1 over square root of 2, 1, 1. Okay. I mean, technically you can put the 1 over square root of 2 in there, but it's just makes it easier. Okay. Okay. But if the measurement comes out to be -1, okay, when you act on this with sigma x, okay, the eigenvector came out to be 1 minus 1, then you actually measure the other eigenvector eigenvalue pair, where you have the negative spin of that particular particle, and then you'll get the eigenvector to be 1 over square root of 2, comma 1 over square root, negative 1 over square root of 2. In fact, I'm going to write this so that it's more clear that this is not the eigenvalue, right? It's just part of the vector itself, right? Negative 1 over square root of 2, right? So this one is actually 1 over square root of 2, comma, positive 1 over square root of 2. Okay. All right. Similarly, we're not going to go through all 3 dimensions. I'm going to actually probably give you guys homework to play around with this, right? You're going to see that the eigenvalue, eigenvector for all 3 of these is always going to be plus or minus 1, but then they have the depending on which operators you're talking about, they'll give you a different eigenvector back up. Okay. All right, should I do this derivation today? Let's not do that. In 1 minute. That's going to take me more than 1 minute to do. So I think that's all I want to cover today. And then on Monday, we'll start off with the other version, the how we can deal with these infinite dimensional operators and still get some clear mathematics out of it. Can have rotational operators. Well, you can change the system, but if you want to have a measurement or an observable, that has to be Hermitian, yes. Thanks. Let's see.